So today we will be talking about DFA minimization. So we have learned how to build DFAs and NFAs for certain languages. Now we are interested in studying how to minimize the DFA, or how to come up with a DFA that has the minimum number of states for a given language. Now, in this case, this is an example. So, the very first thing that we do is getting rid of any redundant states or unreachable states. So, any state that is not reachable, we can easily eliminate that. Right? So, which states here are unreasonable? Unreachable, sorry.
Keep five. It's both unreasonable.
Yeah. Well, in fact, okay, so this is unreachable. But what will make us, or what will result in the creation of an unreachable state? Like, if you are trying to construct a DFA manually for a given language, you're unlikely to create an unreachable state. But unreachable states may be created when?
From an NFA.
Yeah, when you are converting, when you are running a certain procedure or algorithm, like the subset construction, you may create unreachable states. That's if we do it the way we studied it in this course. Like I said, when we did subset construction, there is a way of doing the conversion from an NFA to a DFA without creating unreachable states. In fact, by only accounting for the states that are reachable. You start from the start state and you only process the states that are reachable. And like I said, there is an example that I did in the compiler class, and it's in the recorded lectures for the compiler class. Anyway, so now we can get rid of this unreachable state. So this is an easy concept. Now let's look at what's left. Now, how can you, let's see if someone can minimize this manually without studying any procedure for minimizing a DFA. How would you minimize this manually? What do you think the minimum number of states that you need is?
You can combine Q3 and Q4 since it takes the same requirements to get there.
Okay. Same requirements, yeah. So you have two options here, 0 or 1. You get to Q1, Q2, and then to Q3. It's it takes you up. You need a 1 from either Q1 or Q2 to get to Q3 or Q4. So you can combine Q3 and Q4.
Does Q1 loop on 0 too?
No, it's we did not. Yeah, we did not specify the 0. Okay, so I think it's, yeah, so there is a transition, thank you. So there is a 0 transition from Q1 to Q1. So in this case, you can combine Q3 and Q4. What else? Can you combine Q1 and Q2? Why not?
Because they have a different requirement to get in.
Okay, there are two ways of getting to Q1 or Q2, but once you get there, what happens afterwards is going to be the same. All right, so if I do this, Q0, then Q1, 2, then Q3, 4, and this is an accept state, and this is a 0, 1, and here I loop on a 0 and then a 1, and then this is a 0 or a 1. This is an equivalent DFA that uses 3 states instead of 5. Now why? Let's try first to rationalize this. What's this language here? So we need a 0 or a 1. It's like saying you first need a 0 or a 1. Then you will need a 1 to get you to an accept state. And if you get zeros, you'll stay there in this intermediate state. So a 0 or a 1, just any symbol, can take you to the intermediate state. And as long as you are getting zeros, you stay in the intermediate state. If you get a 1, you go to an accept state. And once you get to an accept state, you are there forever. So this can also be done using this. Oh, so this is constructing an equivalent DFA, minimizing the number of states by inspection for a specific example. This is not very interesting, from a practical point of view. You will need an actual algorithm, an actual procedure that will always work. It's not. We have inspected this 5-state example and we managed to minimize it. What we are interested in is a procedure, a systematic procedure for doing the DFA minimization. In fact, there is a procedure, and it's not that complicated. The key idea in this procedure is to first divide the states into 2 equivalent classes. So the first equivalent class has the accept state. So you have the F, which has Q3 and Q4 in it. And the other equivalent class is the non-final states, which has in this case Q0, Q1, and Q2. Why this? Because we know that accept states are different than non-accept states. There are 2 different kinds of states. And what we're looking for here is we're looking for equivalent states that we can merge together. And since we are looking for equivalent states that we can merge together, we can never merge an accept state with a non-accept state. They're 2 different, they're fundamentally different, they're conceptually different. You cannot merge an accept state with a non-accept state. So you put this in one class, one equivalent class, and this is, you put final states in another equivalence class. Now the key idea in the procedure is that you assume that states are equivalent until you prove that they are not equivalent. So it's kind of counterintuitive. You may have expected the procedure to assume that the states are distinct, then you prove equivalence. No, this procedure works the other way around. It does not assume that the states are distinct, then it proves equivalence. It does it the other way around. It assumes that they are equivalent, then it proves that they are distinct, that 2 states are distinguishable. And once you prove that 2 states are distinguishable, each state should be put in should be placed in a different equivalence class. So initially we have only 2 equivalence classes. So we are assuming initially that 3 and 4 are equivalent, 0, 1, and 2 are all equivalent. Then we will study the relations between them and see if we can see which ones are not equivalent or are distinguishable. So the key idea is distinguishable, identifying distinguishable states. So I will study the relation between Q3 and Q4. Then I will study the relation between all pairs of states in this equivalence class. So I will study the relation between Q0 and Q1, the relation between Q0 and Q2, the relation between Q1 and Q2, and initially, I will assume that they are equivalent, all pairs are equivalent or indistinguishable. So I will put an I. What does the I stand for here? Indistinguishable. Indistinguishable. So the I stands for indistinguishable. So, or equivalent, indistinguishable or equivalent is the same concept. Okay, so now I just look at the transitions for Q3 and Q4 and see if they are indeed indistinguishable or distinguishable. So now, Q3 on a 0 goes to Q3. Q3 on a 1 goes to Q3. Q4 on a 0 goes to Q4 on a 0 goes to Q4, and Q4 on a 1 goes to Q4. Now, does this mean distinguishable or indistinguishable?
Distinguishable?
No. In fact, it means indistinguishable. Why? It means that they are indistinguishable. Why?
Because either input takes you to the same.
Takes me to, on a 0, Q3 takes me to Q3, but Q4 takes me to Q4. How can this be indistinguishable? In fact, it is indistinguishable, but why? It means that at this point they are indistinguishable. Why? Yes?
Because you don't know whether it took Q3 or Q4 to get there?
No. Under what logic? Yes?
They both loop on themselves with a 0 and a 1.
No. Yes?
You can substitute Q3 for Q4 or vice versa, and the rules look the same.
Yeah, exactly. The key idea is that we are assuming that at this point, Q3 and Q4 are indistinguishable. So this is the key idea in the algorithm. At this point, I haven't proven that Q3 and Q4 are distinguishable. So I am assuming from the algorithm's point of view, it sees Q3 and Q4 as the same state at this point. It cannot distinguish between them. So at this point, I can replace this with Q3. Why? Because they are indistinguishable. The algorithm has not detected any kind of difference between Q3 and Q4 yet. So the algorithm sees them the same at this point. Similarly, the algorithm sees 0, 1, and 2 as one state at this point, as an equivalent state. Like I said, this is what may be counterintuitive about this algorithm, is that it assumes that states are equivalent until proven distinguishable. Okay? So this means that it will never prove that Q3 and Q4 are distinguishable, and they will remain indistinguishable. Now, what about Q0 and Q1? Now, Q0 on a 0 goes to Q1. Q1 on a 0 goes to Q2. So, okay, maybe I should write it. Q0 on a 0 goes to Q1. Q1 on a 0 goes to Q2. Is this distinguishable or indistinguishable?
Distinguishable.
Indistinguishable. Because at this point, the algorithm sees Q1 and Q2 as equivalent states. So the algorithm doesn't know that Q1 and Q2 are different. It considers them at this point to be equivalent, indistinguishable. So given this, Q0 and Q1 are still the same. Now, what if I look at the transition on a 1? Q0 on a 1 goes to Q2. Q1 on a 1 goes to Q1 on a 1 goes to Q3. Now, is this distinguishable or indistinguishable? Q2 and Q3, do they belong to the same equivalence class or not? No. They belong to two different equivalence classes, so this is distinguishable. So now I change the relation between Q0 and Q1 to a D. They are distinguishable. Okay? Now I do the same thing for 0 and 2, and I get the same result, right? On a 0, This goes to 1 and 2 goes to 2. So this is indistinguishable. On a 1, comparing Q0 and Q2, 0 goes to 2 and 2 goes to 4. Are 2 and 4 distinguishable or indistinguishable at this point? Distinguishable. They belong to two different equivalence classes. One of them is accept and the other is non-accept. So this is distinguishable. It means that 0 and 2 are distinguishable. Now, what about 1 and 2? One on a 0 goes to 2. 2 on a 0 goes to 2. Is this distinguishable or indistinguishable? Just look at these. Are these the same or not? They're the same. So this is indistinguishable. Now, what about transitions on a 1? So we're comparing Q1 and Q2 now. On a 1, Q1 goes to Q3, and Q2 goes to Q2 on a 1 goes to Q4. Now, are Q4 and Q3 the same or not?
They are.
Yeah, from the algorithm's point of view, they're the same. There's still an I. There is still an I. So the algorithm sees them as two equivalent states. They belong to the same equivalence class. So the algorithm has not been able to distinguish between Q3 and Q4. So this is like the same. So I can replace this Q4 with Q3. So now this I will remain an I. We couldn't distinguish. Because they go, for all transitions, they go to either the same state or to two states that belong to the same equivalence class. They either go to the same state or to two equivalent states. Now this algorithm terminates when we can no longer make changes. So if I look at, I need another pass to make sure that this I will not change to a D. Because changing these from I to a D may change this to a D. Now, if I do it again in this case, for Q1 and Q2, in fact, the relation between Q0 and Q1 and the relation between Q0 and Q2 is not going to change this. Because this on a 0 is going to go to Q2, Q2. So this is the exact same state. So this has nothing to do with equivalence. Q2 is Q2. Here, Q3 is equivalent to Q4. This did not get impacted by this change that we made here. So the I, even if you do a third pass, of course the D will never change to an I. Once a D, it's going to be a D forever. Once you distinguish, they are distinguishable. They're not going to become indistinguishable. So you can go from indistinguishable to distinguishable, but you cannot go in the other direction. So in the third pass, this is a D, this is a D, this continues to be an I. Okay? Any questions? Now this is a fixed point algorithm. A fixed point algorithm terminates when you can no longer make any further changes. So here, this will never change. And this, because we did two passes, the last two passes gave the same results. So one more pass is not going to make a difference. So we know that we should terminate. Now I'm going to show you an example where we, in fact, we need multiple passes, and the changes that we make in one pass affect the changes in the next pass. Now, before we move on, so what did this algorithm tell us? It told us that Q Q3 and Q4 are indistinguishable. And it told us that Q1 and Q2 are indistinguishable. So indistinguishable is equivalent. So this is equivalent. And it told us, so in this algorithm, it assumes that they are equivalent, but it couldn't prove that they are not equivalent. So they remain equivalent. Here, for the relation between Q0 and Q1, it assumed they are equivalent, but then it proved that they are distinguishable. So they are not equivalent. It has proven that they are not equivalent. So now the output is Q3 and Q4 are the same state. So Q0 is distinguishable from all states. Q0 is a distinguishable state. Then Q1 and Q2 are equivalent. We couldn't prove that they are distinguishable. So this is a Q12 state. And Q3 and Q4 are also equivalent. Okay. Now, of course, this is an accept state. And how do we figure out the transitions? Q0 on a 0 or a 1 goes to the merged state Q1, Q2. And then what does the 0 here do?
Loops on itself.
Loops on Q1, 2. And what does the 1? The 1 takes you to the accept state. And what are the transitions in the accept state?
You just loop on 0, 1.
Loop. Okay, so this is a systematic procedure that led to the same result that we figured out by inspection. By inspection, we could tell that Q1 and Q2 are equivalent, Q3 and Q4 are equivalent, but this is a systematic procedure that reached the same result, but in a kind of counterintuitive way. It just assumed that all accept states are equivalent, all non-accept states are equivalent. Then it analyzed the transitions from each pair of states. If there is any difference in the transitions, then these two states are distinguishable. If there is no difference, then they are if there is no difference, then they are indistinguishable. So what we looked at is where we go. So when you analyze two states, like Q1 and Q2, whether they are equivalent or non-equivalent or distinguishable or indistinguishable, you see what the transitions are out of them. Transitions out. You don't care about the transitions in. So you look at the out transitions, where they go, where do they go? And if on every symbol they either take you to the same state or to two equivalent states, they are indistinguishable. If on one symbol they take you to two states that are at this point in the algorithm distinguishable, then they are distinguishable.